So, hello everyone. Welcome to the second edition of Cybersecurity Day. In this workshop, we're going to dive into reverse engineering and forensics. We're going to discover these two fields. We're going to do a couple of challenges or labs together. Some of them you guys are going to do alone. And if anyone can solve all of them, you have a free lunch, okay? Good. So again, that's me, if you didn't come last week. My name is Moabid. I'm 22 years old. I'm a sportsman, writer, researcher, and meme dealer. I'm 42, school graduate, a CS student at DHBW Mannheim, point of sale system engineer at Schwarz, part-time vocal here. You don't see me most of the time, but I'm also working here. So, yeah. And League CTF team founder and captain. And one of my team members helped me today to make the challenges for forensics. Thanks, Abdurrahman. Okay, so what do we have today? We have reverse engineering. We're going to start with a small introduction to revving or reverse engineering. We're going to do a little bit of static analysis. We're going to understand what does it mean and how can we perform this. Later on, we will have to take a look into dynamic analysis. What does it mean? And how it can play with static analysis to help us understand the behavior of binaries and different types of systems. Later, this lecture, we're going to have a little bit of demos. We're going to try to perform a little bit of static analysis and also dynamic analysis on a binary. Then we're going to know what does constructing code means and how can it help us understand the stripped binaries and the extremely obfuscated code. Last but not least, we're going to get to know that reverse engineering is not only for binaries, it can also be performed on interpreted languages, for example, Python. And at the end, we're going to dive into some protection mechanisms to protect our code against reverse engineers. In the second hour, we're going to do a little bit of forensics. We're going to understand what does it mean and what is it today. Then we're going to dive into the three main categories of or subcategories under forensics. We have network forensics, disk forensics, and memory forensics. I prepared a couple of challenges in these, and yeah, at the end, a couple of resources for you guys and a small slide for next week. So, what is revving? Who can tell me here what is reverse engineering just from what we had last week? Come on, guys. Okay. Leave the mic with you, okay?
Retrieve the behavior of code or the source code out of binary file or some executable. You can do it either with decompilers or GDB. I think that was some mentioned. And you would use it for determine if you have a Trojan or if you see a curl request on something and it's just some calculator. You mentioned that, I think. Yeah. So it is malicious for sure.
Good. Just leave it, close it, and leave it with you. Okay, so why do we have to learn reverse engineering? Well, if you know reverse engineering, then everything is free. You don't have to pay for any software. I'm not telling you guys to do this kind of stuff. This is bad. You always have to do the good stuff, but I'm just letting you know. Yeah, it helps you also understand how to write a better code, because if you understand it from the CPU perspective, which means the machine code, you're going to be able to write the code that the CPU will understand faster, perform faster, and better. Also, going back to this point, what I said last week, it's a skill. It's not really a category. It can be intersected with a lot of other fields, including crypto, forensics, and web, or yada, yada, yada. It's also a fundamental part of security. It doesn't matter whether you're going to work in as a malware analyst, whether you're going to work as a pen tester, you will always have to read someone else's code and understand its behavior. Okay? Yeah, and a small meme. We will start with static analysis. Do you guys know what does static analysis mean? Anyone? Okay. Please.
Hello?
Yeah.
I think it's when you take the binary and don't run it, when you look at maybe you decompile it, look at the code, what it looks like, and not what it actually does when it's running. Like when it's running, it's something else.
Exactly, exactly. So when we talk about static analysis, we always talk about a binary when it's still, when it's still not running. We didn't run it, we are not looking into its behavior on the runtime. It's statically looking at the binary, which means you can look at the file structure, you can identify which type of file is this, you can identify the code, you can try to disassemble the code, you can try to even decompile the code if you can. And during this phase, it's really, really important and crucial to understand the anatomy of the files. Every file has an anatomy. For example, in Linux, every executable is an ELF file. And in Mac, we have Mac-O, and on Windows, we have PE files. Understanding these type of files and how they are understood by the system and executed gives you a hint about its behavior before even running it. Okay? So again, static analysis, taking a look into the binary. When it's still binary, not run yet, it's still a file. You just try to understand and get as many informations as you can on the, yeah. Does it make sense? And during this static analysis phase, we're going to take a look into disassembling and decompilation. But before this, we have to understand how binaries are actually created. For example, these ELF, PE, or Mac-O, all of these are executables. All of these are the output of a C file. A C file can be compiled on multiple platforms, but the executable not going to be the same at the end. It's going to achieve the same behavior if it's cross-platform, if you take into consideration the anatomy and the system you are running this on. But it's and understanding these steps will help you go back, because again, reverse engineering from the behavior, from the executable, you're trying to go back to have an idea how the source code looks like. Okay, so from C to machine code, we always have first the pre-processing phase. You guys know what is pre-processing? Again, Mike. What is pre-processing? All right.
Hello?
Yeah.
Okay. So it's when we change the macros in our code, include headers to the appropriate.
Exactly, exactly. So when you do in your code the includes, or when you define your macros, these stuff will be changed to their original values in the pre-processing phase. Also your libraries, like they're going to be taken from the binaries that you have, like the libraries that you have in your computer. They're just going to be taken there and just added to your code. Does it make sense? Then we have the compilation phase. The compilation phase will, this is the first compilation phase. It's going to turn our code to an assembly code. Believe it or not, but any C code can be compiled with the GCC to an assembly version of it, which is going to be later on turned into machine code. From one perspective, you can think of assembly as machine code because it's just a little bit readable format of machine code. But at the end, if you translate byte by byte what it's doing, it's going to give you exactly the output file, which is pure binary. Okay? The last step is the linker. Do you guys know what is the linker? Yeah?
Hello? It's kind of a reference manager, so it would like take all the pointers to functionalities, I would describe it, and put them together. Like if you want to compile different files with makefile, it runs linker errors if it doesn't find resources that you say that they are declared there. So it links the naming or the pointer to the logic or to the thing we actually want to point at.
Okay. Yes, and linker is basically from another perspective. You can say that when you compile object files are a direct translation of your code to binary. So direct translation, your code from C to binary. In the linker phase, for example, if you have some other libraries, if you include, for example, printf and you use it and it doesn't exist in your code, during this phase, this binary is going to be searched and linked with this specific call that you are calling. So from one sense, it's yes, connecting the pointer that you have of libft, for example, because all the functions are basically pointers, right? They are all reside somewhere in the binary, and all of them can be accessed via pointers. So during that phase, basically, you're just making this linking. That's why we call it link. It's linking between different symbols that make up your whole executable at the end. Okay? So opcode, now we're going to try to go backward. I mean, at the beginning, we went forward. So we started from C code, and then we got so down to the point where the CPU can understand what we wrote, which is the opcode. Now, if we want to go back, we start always by disassembling. Disassembling means going from opcode to assembly. And in this picture, I linked just a picture of, do you guys know what is this? I mean, which tool is this? Which tool does what I'm showing in this picture? Yeah? No, this is the GDB. This is the GNU debugger. And as you can see here, I'm just running it. And it's on the runtime, it tries to disassemble whatever the code where we are right now. Why this kind of debuggers are a great tool for us? Because they interrupt the CPU on the runtime, and step by step, you understand what does the CPU execute. Like literally, instruction by instruction. You understand every little detail what your CPU is doing. And also, it gives you some other quirks. For example, you can inspect the memories, you can inspect the heap, you can also disassemble on runtime. For example, you know a specific instruction going to be run at a specific address. You can, starting from this address, disassemble whatever code is after and before. Okay? Now, we're going to go one step further. Here in the previous slide, we went from opcode to assembly. Here, we are jumping from opcode directly to a decompilation. As you can see on the right side, it's kind of a C code that represents the binary. This is from Ghidra. And on the left side, it's kind of the disassembling. So Ghidra gives you the ability to see both the decompilation and disassembling, because the decompilation is not always correct and doesn't always represent one-to-one our binary, especially if it's obfuscated, if the symbols are lost, which means when we strip the binary, and also when also when we want to inspect some other sections that are not really taken into consideration when you do it with GDB. So again, Ghidra just gives you an overview over everything, a little bit of decompilation, a little bit of disassembling. Also, you can see here the symbol tree, which contains all the functions in the binary. And yeah. Don't worry, we're going to take a look ourselves into IDA. We're not going to use Ghidra today. I will personally use IDA. And we're going to try to decompile our own code and see how it's going to look like, okay? Okay, dynamic analysis. What is this? With these fundamentals, I mean, with the fundamentals we had before, now we're going to take a look into GDB. As you can see, GDB can be used in both. You can use it to disassemble your code, and you can also use it to understand its behavior on the runtime. Why do we need to understand the behavior on the runtime? Give me like an example why or how it's going to help us understand it on the runtime better than doing it statically. Any example? Yeah?
So working with pointers, for example, is very important. If you work with pointers, doing it dynamically is the only way actually you can really follow it step by step. And since you mentioned that everything at the end will be basically something on the memory that is pointed to, that is the way to go to understand step by step what is happening in the source, so behind the scene of your source code.
Good, good, good. Yeah, as you said, pointers. Oh, you want to say something? Yeah.
I thought that maybe we are interested in a specific functionality and we just want to capture that part. And we see
What are the specific functionalities that are only on the runtime and we cannot see them statically? It's easy. There?
Hello? Maybe the program is pulling something from the internet, something that we can't see.
Good.
Or maybe there's even encrypted data in the program
Yeah,
that it will encrypt on runtime.
Yeah, good. Yeah, that's a really good scenario. But you went so far. There is something extremely easy that you guys forgot. What is dynamically allocating a memory? When you malloc something, you cannot see it on the statically because it will be allocated and giving to you on the runtime. This is one example. A second example is, as he said, for example, if the malware is trying to connect to the internet, you cannot really see this statically. I mean, you can see that it's trying to connect to something, but probably you're not going to see the traffic going in between. Also, there is some types of mechanisms where you encrypt your binary and decrypt it on the runtime, which means if you try to look at it statically, you're not going to see anything, or better say, you're not going to understand anything because the binary will be encrypted and it will be decrypted on the runtime. I mean, even in this case scenario, you can still do some analysis, which means you're going to understand which part of this binary is actually doing this encryption and decryption, because it doesn't make sense that the whole binary is encrypted because the computer is not going to understand it. As simple as this. Okay? Does it make sense? So GDB, again, it's a tool to interrupt the CPU on the runtime. Interrupting, you guys know what is interrupting? It's one of, yeah?
It's a special functionality by the CPU that will interrupt the current flow, whatever is running, and replace the process with something that's predefined as an interrupt handler.
Yeah. So interrupting, basically, it's an instruction called int3. This instruction stops the CPU process, and it's also a signal that's sent to stop the flow of the program and allows you to inspect some different components of the binary on the runtime. For example, you can see the registers, which values do they have on this specific time. This is also one thing that you cannot see during in the static analysis. Let's say, for example, this specific function is doing some sort of, I don't know, random value generation. This value, you cannot see it on statically, but if you do it dynamically, you can follow the flow of the code and reach the specific function and inspect the registers. You can see, for example, that the return value is in REX, and you can just see it directly in GDB, and you're good to go. Something like this, you cannot do it statically. Okay? So as you can see, it's always this mixture between the analysis, I mean the static analysis, and the dynamic analysis that really helps us understand the behavior of the binary. Okay? And also mastering this is really fundamentals. I only mentioned here GDB. GDB is meant for Linux. For Windows, there's also WinDebug. There is also x64 debug. There is a lot of other tools that are meant to achieve the same behavior, but on a different platform. Also, you guys know LLDB for Mac. Yeah? Now we're going to do a live demo. Please boot up your computer. And yeah, let's have some fun. Does anyone here not have everything ready? Okay. Is it running, or are you building the image? Oh, no. Okay. You can follow along with someone beside you. Does the rest ready have the image ready? You don't have to clone anything. Just do you have the image ready? Okay. Let's start with, or let's do something. Everyone here cloned the repo that I said before, or someone here didn't clone it? Yeah, the one I showed. I will show you the repo again, clone it, and let's start, please. Yeah. Here is the repo again. Go to this repo and clone it, okay? And go to the folder under rev, which called demos, okay? You should see something like, oh, oops. Yeah, you should see something like this. And here I have 3 different files. We're gonna take a look first at just main.c. It is just a simple hello world written in C. And I'm using this image because I want to compile it to x86-64. It's the architecture which is widely used in the computers. Yeah, so this is the code we have. Is everyone following up? Who have IDA or Ghidra installed? Okay, good. Yeah, I mean, better, because we're going to do both static analysis on this binary and also the dynamic analysis on it. For dynamic, you would have to be in the image. Statically, you don't have to. Okay, if someone is still doing it, just look at here. We're going to do it together. Just look at what I'm going to do now, because later on, you're going to have to do challenges anyways, and I'm going to give you more time, then you can clone the repo and try to solve the challenge. Yeah? Yeah, I mean, Ghidra or IDA, if you didn't install Ghidra yet, just install IDA. It has nothing to do with your Mac chip. Doesn't matter if it's a Silicon or Intel. So yeah, you can just download it from the internet. But we will get started, okay? So this is the binary we have. Just please look at here. This is binary we have. We're going to compile it with GCC. What we got here, file, this command allows us to inspect the header of a file to check which type of file is this. I'm going to inspect EWEA out. As you can see, it's an ELF 64-bit file. You see afterward, you can forget about the Py executable. Afterward, you see that it's x86-64. This is the architecture it was compiled in. If we try to compile the same thing on Mac, it's going to show us their ARM, because this is the architecture used by the silicon chip. Also, it's dynamically linked. As I said before, it means it's going to link dynamically the symbols that we are using in the binary. In our example here, we have printf. And yeah, the other informations, you don't really need to know about them, except not stripped. Do you guys know what is the stripping a binary? What is stripped and not stripped? Not stripped means the binary still has its symbols. Symbols means you can still see the function signatures. Non-stripped, stripped means you're not going to be able to see this. So even the main going to be lost. The only thing you're going to be able to see is the entry points. Some static analysis tools, for example, IDA, can identify still the main function, even though it was stripped. But all the function names going to be lost. Okay? So basically, we have 2 types of binaries. We have stripped and we have not stripped. Stripping something means removing something. Not stripped in this example means all the symbols are still in the binary. Symbol is the function signature as an example. So the function name, like right now, we're going to try to decompile this binary. We're going to go directly to decompilation. If we decompile this binary, okay, I don't have any a function here. Wait, let me just add the name of a function just so that we understand. Yeah, you can do it yourself. I mean, there is a tool, command line tool called strip. You can use it to strip the symbols from a binary. It doesn't break the binary when you strip it. So just an example here, I'm just gonna do like, for example, void, I don't know, printer, and it's not gonna take anything, and it's just gonna do printf. I am stripped from my symbols. It's do like this, and here, bum bum bum. You can also do like this. No, we're just gonna call printer, and we are done. Let's do gcc main.c. We're compiling this again, and no, we don't want to run it yet. Let's do a file. Again, as you can see, it's not stripped because we just compiled it. We didn't strip it yet. And now we're going to try to inspect it under the scope of decompilation, okay? I'm going to start IDA. If someone have IDA already installed, he can follow along. Otherwise, yeah, it's not going to be much stuff. Going to start. Okay. Technical issues, but we can do it on the web. There is a tool called dog bolts. This tool also allows you to decompile a binary. So I'm going to upload here the binary we had right now. Documents, Cybersecurity Day, lecture, yeah, lecture, rev, and then demos. Yeah, we have the A-outs. So this decompiler here, we're going to try to run it through multiple different providers. For example, Ghidra, Binary Ninja, Hextrace, and Anchor. Hextrace is the company that owns IDA. It takes a little bit of time for the others, but as you can see for Binary Ninja, it's already found some stuff. Most of these stuff here are the stuff that C is doing in your underneath, so in the background, stuff that you don't really see when you are writing C code, but in the decompilation, the decompiler tries to decompile almost everything. Any readable and executable code within the binary will be decompiled. And if we take a look here, we will find our main. As you can see, it's still called main. We can see our print hello world. Also the name of the function, you see it's still called printer. Does it make sense? Now, let's try the other scenario. I'm not sure if strip is installed. Okay, it's installed, strip all, and A-outs. Yeah, so now if we do file A-out, as you can see, now it changed to stripped. Now, we will try again to open this file from the same decompiler. Again, open in the same file. Okay, let me just reload this. Didn't seem like it liked it. Okay, let's wait a couple of seconds for it to just try and decompile it. And now we should not be able to see the symbols, including the printer function. It will be changed to the address of the function. We will see it in a second. Okay, we can see it already here. We don't have to wait for the others. As you can see, it was changed with the offset, exactly the offset. Not really the address, but the offset. Because when you run the binary, if there is like a specific protection mechanisms enabled, the main address where everything starts is going to be dynamically generated on the runtime. You don't have to think about this. For now, just think about this is the address, okay? It's the offset, but think of it as the address. 1149 here. I'm going to close the rest. See it here? So as you can see, we tried through, the web, you can feel free to do it through IDA if it worked with you. Otherwise, there is Ghidra, there is also Binary Ninja. There is many tools that allow you to do this decompilation. And all of them achieve the same thing. They have different algorithms behind it, but in the end, all of them are doing the same thing. Okay? Does it make sense? Good. Now that we try to decompile this, we're going to try to disassemble it. Okay? And for this, I'm going to use GDB. Sorry? The microphone, please. Don't close the microphone afterward, just leave it.
Okay. My question is, why would we strip it from the first place? What's the point?
Okay, so the whole, like always when you write code, your target is to make it as hard to read and as bad as it looks like, so that someone trying to do this reverse engineering to crack your code, to use your software without a license, you should give him a hard time. I mean, it's really impossible to protect it 100%, because as long as you have a direct access to the binary, there is always a way. But our job is to make it as hard as possible and to make his life as nightmare as possible, just for him to give up and to not crack our code. Okay? Does it make sense? Stripping it is just one of the things you can do, because then the name of the functions are lost, and it's really hard to understand the behavior if you don't know what does this function do from the name.
So it's a security mechanism.
Yes, you can also consider it as
And do
security.
we do it manually like this after compiling our code?
Yeah.
Or?
Yeah.
Okay, thank you.
If you want even more symbols, you can use -g. I think you guys already know -g. It adds also the debugging symbols on it. And with the debugging symbols, you can retrieve the whole source code back. You don't even have to decompile it. Just through GDB, it can retrieve the whole source code back with a function called list. Anyways, can we go, Mike, there?
Hello.
Yeah.
Can you compare it with OFast?
Sorry?
Can you compare that like with OFast?
No, because OFast, it optimizes the code. It doesn't lose the symbols, it optimizes the code. Optimizing the code means, let's say you are trying to do some arithmetic, mathematical things. These things can be shrinked to the equivalent version of it in a way that it just works the same way. Also, from another perspective, let's say you are calling some functions, or you're using some functions. You're using some functions that are not really doing anything to the output. They are not changing anything. In this case of scenarios, it will also be removed in the optimization. But this has nothing to do with stripping. Okay? Okay. Any more questions? Yeah?
Will stripping break the code into different parts? Not break the code in the logic, but will it distribute it into different files or multiple files and link even file structures together to make it even more messy? Or is it more like, I have some idea about minifying JS. So you will strip, for example, add two numbers together to a function called f or b, and you just hide the human readable way of it? Or is it really like separating it?
Let me go back. That's why it's always good to know the anatomy of the files. So if we take a look into this anatomy, we see that our file is it's split into three parts. We have the header, which has the information about the file, and most of these informations can be read directly with a tool called readelf. Or also when we used the file command, it also did read all these informations from this here. Okay? We have the second part, which is the sections. This section is also split into some more, some other subsections under it. Not subsections, but sub-directories, or I don't know, some parts under sections, including the code. This is where exactly your code resides. And we have the headers. These headers are how you are actually splitting your code. For example, your global variables, they're not put together with your code. Your I don't know, your like the variable which are on the these are on the stack. The variables that are dynamic allocated, they are also in another header. They're not in the same place. And this anatomy helps us understand how this stripping actually works, and also helps us make this code as much unreadable as possible, because your task is to basically remove any part here that doesn't really change the behavior of the code and doesn't really break it. The name of the function is always included there. It's included here. in the section names. It's always included there. We always want to remove this part because it's critical, especially, let's just give an example. Let's say we have a key generator. This key generator is using some algorithm, let's say it's RS4. From just the behavior of the function, it's really hard to spot that this function is really an implementation of RS4. But let's imagine the name of the function is RS4. It's immediately gonna spark the idea that, okay, this is this algorithm. And you can just look at directly where is the key and just break it. You see what I mean? It's always this trying to make the code as much hard to reverse as possible. Yeah, so now we're gonna go back to our binary. I think this was the stripped version. We're not gonna start with the stripped part. We're gonna do it unstripped first, dynamically, and then we're gonna do it stripped. Okay. Let me remove A out and GCC main.c again. And now with GDB, we're gonna start running this thing. If you use the image that I sent you, this is GDB plus a plugin called Pound Debug. This plugin allows you to have a more readable interface. It also shows you the register in every instruction. It also lets you do some more advanced stuff. For example, it has the start command, which is one of my favorite. Start command, basically you're gonna jump directly into the first instruction, which is the entry point. Entry point is where your code starts. It's not the main. Entry point, again, it's not the main. It's the function that actually starts your main. Okay? Again, entry point, this address is always in your header. Like, again, going back to the anatomy of the file, that's what I'm saying. If you want to really master reversing, and really understand it on a deep level, you have to understand the anatomy of a file. Because I still remember one of the CTF challenges that we did before, the name of the challenge was technically correct. In this file, the binary was so broken to the point you cannot decompile it and you cannot use GDB with it. But it was working. The CPU was actually executing it. And this is one of the tricks you can do to make the life of a reverser much, much, much harder. Okay? Again, this is simply talking about ELF files and binaries. Going forward, you have to take a look into some other formats. You have to take a look into some other languages, how they are changing your code, how they are compiling it, how it can be retrieved back. All of this plays a role in understanding like reverse engineering in depth. Okay? Now, because we have still the symbols, we can do a function called info functions. This info function command, it's equivalent to this in Ghidra. So if we go back to Ghidra, you see this here, symbols tree. We are doing the same thing. Just the only difference, Ghidra is smart enough to identify if a chunk of code is actually code and gives you like this func and then the address. GDB cannot do this. GDB just looks at the code. If it finds a readable symbol, not stripped, again, readable symbol, it will just put it there. Going back here. Okay, going back here, as you can see, we can see printer and then main. See both? Now, let's try to strip it. Or let's work with this a little bit. Now that we have actually symbols available, we can disassemble directly. We can do this as, which stands for disassembly, this as main, and this directly did give us the disassembling of the main. So this is exactly how our main function will look like on the assembly level. Okay? We will take a look into how to do the same thing in stripped environment. It's much harder than this. It's not that easy, but we're going to take a look into it. Okay? Yeah. So this is it. Yeah. Sure.
Pass me the mic, please. Sorry. So I just run this command, but now apparently it's couldn't get registers. Is it something related to now the?
What's?
Yeah, it was the same for me. I just
Can you exit?
Exit the whole. Now
Yeah,
I'm in
exit from this. Okay, just to mention something, I think I know the problem. So basically, if you run GDB without this dot and slash, it's not going to be able to run it correctly.
I did it without.
Yeah, that's why. Yeah, I knew it immediately because GDB it's attached, like it's a separate process which is attaching itself. Going back, did you guys, everyone here did philosophers? Okay, so if you go back to philosophers, you learned about processes. GDB works the same way. It's a separate process that attaches itself to the a.out. If you want to run a.out, you cannot run it like this. You have to run it like this, right? So just do this and it will work.
Okay, thank you.
Yeah. You can also see it from here, reading symbols from the name of the file. Okay? Again, info functions. We can see here printer and main. And if you do this as, we can also do it with any function here. This is the printer. And this is the main. Also, now we can go even further and use the specific quirk of GDB, which is actually stopping the execution on specific times. Let's stop at the first instruction in main. To do this, we always use a command called break, which means a breakpoint, like, break, and then you're just going to give it main. If you do break main, it's going to start at the first instruction in main function. Like this, it did attach already a breakpoint there. Now, if we run it, R stands for run. Okay, I forgot to start. Always remember to start with the binary, because when you start, it will give the... Get registered. Wait, 1 second. Does everyone receive the same error? It runs fine? Okay. Let me try to do something. Which function doesn't exist? 1 second. Now I'm starting GDB without the add up, and if we do start, okay, it seems like there's a problem with my image, my Docker image. Yes. I will take a look into this during the break, okay? But normally, for people that the stink worked with, it should run GDB and stop in the first instruction of main. And I think it's even in this slide here. This is the first instruction. So it will exactly looks like this. This is the first instruction. This is the address. It's stopped here. And now, if you want to move slowly, step by step, you can just use S. The S command allows you to just step one step. Continue one step at a time. If you want to go directly till the end and continue to the next either breakpoint or the end, you can use C, which stands for continue. Okay? Yeah?
What's the difference between N, so for next, I think, right, and S? So
N?
So N,
There is
I'm referring to LLDB, but I don't know if it's applicable for GDB. And for LLDB, we had N for going next. Is the S referring to the functions only? So to step in and then to go to the next functions, or?
Yes. S stands for instruction, so it's the next step of the instruction. Next is, I never used next, to be honest,
Okay.
but I think next is for the next function. I've never used it, so I can tell you for sure. Most of the time, you only use S for like stepping step by step. You can use fin if you are in a function and you want to return directly without like stopping. So let's say we are in a function called printer. If you do fin, we're going to go back to the call of the function in main. Okay? Yeah, there?
N is similar to step, but if the next instruction is another function, and skip the function and go to the next instruction.
Okay, that's something new, also for me. So probably also here, I couldn't test it, but it should be the same thing again. Okay. 10 minutes. Okay. Didn't really solve the problem, so I'm just gonna add back my GDB inits. Nice. Okay, nothing is. Anyways, we have some other commands. Actually, if you run the binary in a normal behavior, sorry about this, but if you run it in a normal behavior, it will give you 3 sections. The upper section is going to show you the contents of the registers, if I remember correctly. The middle is going to be the disassembling, and down going to show you the stack. So at every step, you can view exactly what is happening in different components of the binary. Okay. You can also use a different function, like for example, info registers. This should show. I mean, the program didn't start, but normally, if the program is running and you do info registers, it shows you all the registers and the values that they contain. Some more advanced method we have also X, which stands for examine, and this allows you to examine a specific address. Let's say, for example, we have an address called, I don't know, 5555, then 4, then 3A. Like if you want to examine like this address and see exactly what is going on there, we can use X. X can also be used with some customization. You can inspect, for example, only the 10 bytes after it. Like this address, 10 bytes, you're going to view them with this command. If you want this command to be directly disassembled to instructions, which what I was going to show you guys in a stripped version. In stripped version, you don't have symbols, so you have to look at or you have to disassemble everything yourself. So what you do, you always do starts. So basically you start your binary. It will jump to the first instruction. Going back here, it will just jump here to the first instruction. And then you're going to copy this address and do examine. And for example, you're going to examine the next 50 instruction after this. This is how you go. You go slowly through it. I will show you how it should look like. So it should look like this. You will inspect only 50E, which stands for instructions, and then you just give it the address, like whatever the address was there. Doesn't matter. Yeah, please here.
Is the distance between the addresses, so the instructions, same? So is every function stored as a specific amount of bytes, and then the next one the same amount, etc.?
Okay, this is a really good question. You remember what I said before? I said like there is a security mechanism we add to binaries so that their start is always changing. The start will be dynamic. However, the thing that will never change is the offset. Offset means how far is the function from this base. Like right, oh my god. Like this right now doesn't work, but normally if you do vmmap, you can view the memory layout. And this memory layout, the first address is basically the starting point of your whole binary. You can imagine it as 0. I mean, right now if I do just info functions, it will start from 0. As you can see here, no, it actually starts from 1000. And this is like basically the offset from this. But in a normal running systems, the address that most of the time see, it has here like multiple 5s and then has here 40,000, like multiple 5s and 40,000. This is the address you see most of the time. It's also the address that I have here in the example here. I mean, here we are already through the code. That's why the offset is like C890. But the starting point will have here a 4 and here 3 zeros. Okay? You can see this with VMAP.
Okay.
Yeah. Does it make sense so far? Yeah?
You said that the starting point is dynamically, but is it or changing at some point? And I didn't really get where is it changing? Is it changing while the program is running? Is it changing? But okay, but how do I examine then where the function is stored? Because the offsets stay the same. Makes no sense for me at that point. And the other question relating to that is, how can we set that point in code, or is it just set by the compiler, or how does this depend? And is it always the same if we start the program?
Okay, multiple questions. I will start.
Sorry.
It's fine. So the first question is basically you said you don't get the points about dynamically this. Okay, whenever you run the binary, if this pi is enabled and ASLR is also enabled, every time you run a binary, it will have a different address. The starting point is going to be different. Offset is going to be always the same. Throughout the execution of this code, it's going to have the same starting points. But the moment you rerun the code, it's going to have a different address. This is the first thing. Also, this thing is one of the things that makes our life harder. It's not meant for you to make your life easier. So if, for example, you found that a specific function starts from the address 55555, then a specific offset here, and you run it, you'll find that this part did change completely and it's on a different address. Yes, this can happen. And this is normal. This is just to make your life harder. However, again, the thing that never changes is the offset from the starting point. And this dynamically address generation, it's made by the CPU on the runtime. It doesn't happen on the compile time. When you compile the binary, it will just have the offsets. Okay? That's why I said when you run it, it will have a different thing. Because then it will be the job and under the hands of the kernel. Okay. Yeah? Just don't turn it off. Just leave it.
So the kernel just assigns another memory location for the runtime or the running program. So the addresses change.
It's more complicated than this, but yes.
In essence.
Yeah.
Okay.
Yeah. It just assigns a specific address to you. Yeah.
Thank you.
Yeah. You're welcome. Good. Okay. So. Sadly, we couldn't really take a look in depth how this GDB works, but I hope you guys have an idea about it. Also, the famous commands. First one is a start. Second one is run. Third one is continue. We have also step. We have examine. We have info, anything, info functions, info registers, info stack. I'm not sure if this exists, but I don't know. We have also, if you want to inspect the heap, we have heap-v. Space dash v. It also shows you the different allocated memories on the heap, and yeah, this should be it. It's just about practice. Most of this stuff I learned it along the way. I didn't really have a class or anything related to this. Just from doing, you understand stuff. Also, I can give you one good trick. I was gonna show you this trick if my IDA was working, but my IDA is not working. Basically. This is something I always do. Whenever I pick up a binary and I know it's not going to be changed every time, or maybe it's changed every time, I always run the map. I take the first address, I go to IDA, and I rebase my program with this address. Why this is good? Because when you rebase your whole thing with this new address, IDA is smart enough to recalculate all the addresses. And when it's recalculating all the addresses, you can see there exactly where you want to go. You don't have to disassemble through everything step by step. Does it make sense? Let's say binaries have a starting point, right? The starting point, let's say it's 0. Rebasing, which is one of the features of IDA, means you're going to change this stuff so they are changing the binaries. Now, we're not talking about dynamic stuff, we're talking about static stuff. Binary itself is going to be changed. This first address, instead of being 0, it's going to be changed to the value you're going to give it. which is the value we did get back from the decompilation. You see this mixture? You always try to find this spot between dynamically and statically analyzing something. This is what gives you the overview of the underneath. Again, if I was too fast, we open the memory layout with VM map. We take the first address, which is the starting point. We go to IDA, we go to the segment, and we rebase with this new address. Why we do this? Because we now have exactly the right addresses. So if we go back to GDB and we want to breakpoint as a specific part, we have the addresses already in IDA. We don't have to go through the whole thing to find out which address. Do you guys understand what I mean? Does anyone still not understand something? Yeah?
What you just mentioned, using ADA as a tool to see the addresses of the functions, I don't know the terms of it, but
Binary.
binary. Can't you just open another terminal, then displaying the info, so with the the command info, and then picking the addresses and staying, so to say, in the terminal environment instead of taking another tool?
Yeah, but the problem, sometimes you don't want to stop in a specific function. You want to stop in a specific instruction in a function. If you want to do it in a non-stripped, in a stripped environment, you will have to traverse the code. You will have to go slowly, disassemble slowly, then you can retrieve the address where you were looking for. Also, this requires a good knowledge of assembly, because otherwise you're going to be looking from two sides. You're going to be looking here, okay, what is the equivalent of the C code to the assembly, okay, where I can find this. I'm just telling you a trick or how to make your life easier, because I've been doing this for almost every weekend for a long time.
Okay, so ADA is just a tool for us to make this step easier.
Not only this, it also allows you to, I'm just giving you one of the plus things about IDA. I mean, IDA, the first point where we use it is basically for decompilation. Okay?
Okay, thank you.
There's some more advanced stuff. For advanced reverse engineers, they can also do IDA scripting. So, for example, some binaries does some stuff, and you want to actually do some scripting on real time. You want to modify some symbols, you want to retrieve some stuff like this. You can also script in IDA.
Okay, thank you.
Now let's go back to this. Please. Oh, I have it. Yeah. Hello. Yeah. Now, please. Okay. We just did the demo now. Now, is it really this easy? Well, the decompilation is not always right. Most of the time when we strip the binaries and when it's super complicated, when it's working with big integers, believe me, you're not going to understand what is going on. Especially when it has like an algorithm, a crypto algorithm or something super complicated. Also, the data structures are actually lost. This is one of the few things that makes your life more harder. So let's imagine you have a specific data structure. It's just going to be changed to a void pointer, and then all the fields going to be changed to 3 variables or something like this. But the real data structure is going to be lost. However, in Ghidra and IDA, you can reconstruct these back. So when you are looking at these garbage-like values, and you see that there is something that works like a data structure, you go to GDB, you inspect it with a heap-v, you understand, okay, this was actually allocated, you can make sense of it. You know, you see what I mean? You see that this is actually doing this. And along the way, while doing this whole thing, you reconstruct the code. I mean, the decompilation directly doesn't have to be perfect, but you try to make it as more readable as possible, so that when you are looking at the code, you actually understand what is going on. And the reconstructing has a lot of, has a lot of steps. First one, you rename the functions to something meaningful. After you brief overview, you also rename variables. You change the data types of variables, because sometimes you see that there is a specific, I don't know, specific array which is not really decompiled correctly to an array. It's going to be decompiled to a void pointer, and the indexing going to be accessed with a plus sign. So basically, address plus 1, it means address brackets 1, if you understand what I mean. Yeah, I can show you guys one of the C cool tricks. Did you guys know that you can actually, in C, if you do like array and then you do index 1, this thing is equivalent to doing 1 array. These two are the same. Both are compiling. Both are going to be the same thing. Why? Because this thing is in the end basically just the address of R plus 1. So if you write plus 1 at the beginning or at the end, it's not going to change anything. All right? That's why in C, this thing is actually working. Okay, going back to, sometimes binaries are stripped. We talked about this already. It's hard to understand the algorithms this low. Let's say you are used to, I don't know, running some stuff in Python. You just you run RC4 from a library in Python. In decompilation, it's not going to look the same. It's going to be really the instruction that's really made up this algorithm. If you don't understand how this algorithm is actually working this low, you're not going to understand what is going on there. That's why, as a reverse engineer, you have to take a look under the microscope or under the decompilation, literally every algorithm, how it's going to look like after it's decompiled, because this is going to save you time. Okay? Not only this, you have to take a look into different binaries, because the way the translation is working from Rust to binary or machine code is not the same like C. C is considered beginner friendly. Rust and Go and C++, don't get me started. Decompilation is always converted to C. It will never be converted to Rust or any other language. That's why, because Rust has a lot of stuff going in the background, you will have to understand what are these stuff and how to spot exactly the code, which is the logic out of everything. Okay? Just imagine the compilement was meant to be Rust or Go into C. I have already some examples for us, and we will take a look into it, hopefully. The reversing engineering level to decompile the Rust is really high. It requires a lot of practice. It's not impossible, just requires practice. Again, practice. Reconstructing the code, it's not really that easy, especially when you have huge code chunks. That's why Rev is not really hard, it's just time consuming. So if I give you infinite amount of time, you will eventually understand every code, what it's happening, what it's going on, what it's doing. But most of the time during the CTF, you are limited to 48 hours or 24 hours, and you have multiple challenges. That's why you have to practice to the point you can spot the patterns. For example, AES, it's one of the encryption algorithms. If you are familiar with how it's working underneath, you will spot it immediately, even though it will be super complicated from a C perspective or from a machine code perspective. But through practice, you will come across this once, twice, 3 times, 4 times. You will eventually get used to it. Okay? Yeah. So with practice, you can spot the data structures from behavior So we will do demo time. We're going to try to decompile C, but after a question.
I wanted to just clarify, so reconstructing, for example, the data in the sense of data structure would refer to tracking the addresses you have, and then seeing, okay, they are contiguous, so it was an array. Or in the other way, they are not contiguous, but they are still pointing, so to say, to each other. Then you see, okay, it's a singly linked list, right?
Yeah, yeah. Under the decompilation, everything gonna be changed to pointers.
Yeah.
If it's not known, it's gonna become void pointers. Most of the time, not most of the time, sometimes void pointers are a hint that this is a data structure. If it has some other variables under it, and that's how you construct it.
Okay, thank you.
Reverse engineering, especially trying to understand decompilation, is really about finding patterns. You don't have to look through the whole code. There is two types of like going through the code. There is bottom up and there is up to bottom. Up to bottom, you will start from main and you will go through the whole code. Bottom up, for example, it's a flag checker. You guys know what is a flag checker? It's just going to check your input with a flag. And instead of going from main until you find this logic, you're going to start from bottom, which means you're going to start from the print that says error if you didn't guess the flag correctly or if you didn't supply the keygen correctly. This invalid license, for example. You can actually start from that point. And in the huge code base, we always start from that point and we go upwards. We will go quickly through a Rust binary. And our compile, it's just here. Rev, demos, then we have Rust C, main.rc. I will show you the Rust RC. It's just a print, you see, it's just printing hello world. It's not doing anything. And we're gonna try to look at it under decompilation. Okay, I think I have this open. You can choose here. We have main. Again, we just decompiled Rust. If we do file main, which is the output. Okay, right now I'm compiling it on my Mac. You see, it's a different types. Mac O, which is pointing to the architecture that I have on this PC, is a different file, but it just have a different header. The underneath, how the decompilation will work, it's not going to be much different. Okay, it's taken forever. Binary. Binary Inertia also has an option to do it on the cloud. Hopefully I remember my password. Bruh. Man. Okay, this is already giving us what we are looking for. Move this. You see this? All of this is just hello world. This is hello world in Rust. I mean, you can still... Yeah, I mean, Rust is doing the Rust stuff in the background. That's why, let's just take a look how big is this file. It's literally 400 kilobytes for just hello world. Nice. If we compile, let's compare it. Let's compile. That's C. Yeah. Again, ls-la. Look at this. 33 kilobytes to 418 kilobytes. I'm not surprised. I'm really not surprised. Oops. And in the end, Crab is dancing and we are suffering. I was going to show you also C++. It also gives a different output, but you guys can do it this yourself later on. Okay. Also, reverse engineering is not always related to binaries. So yeah, you're wrong on this. We can also reverse engineer Python code, Python interpreted code, and also .bin, the .NET files, no, not files, .NET code, which is C#. And yeah, so it can be projected to some other machines and some other types of executables. Do you guys know that we can actually compile Python code to C? Yeah, you can actually compile Python code to C, and if some sort of Python code was compiled to C, you can decompile it, but it doesn't work with all Python versions. I think this works for 3.8 or 3.7. This tool is called uncompile sex. It allows you to decompile the PyC files and try to get readable Python code out of it. Because Python, under the scope again, it's just bytecode. Okay. Also .NET, you can also decompile it. There is this tool called the dnspy. There is also another tool called lspy. Both of these tools allows you to, from the .NET binaries, get back the source code. Okay. So as you can see, the decompilation, we don't have to do it these days ourselves. It's done automatically or automagically by different type of tools. You just have to know them. Protection, yeah, we have a lot of protection mechanisms. Please don't use Cheetos to protect your home. There's a lot of anti-reversing techniques, but in the end, there are the myths. They just make your life harder. They are not impossible to crack or impossible to reverse. They just require more time and so on. Yeah, so again, protection is just making the job of a reverse engineer harder and more time consuming. We just want him to give up, and that's our goal. Also, anti-reversing is split into two parts. There is anti-dynamic reversing, which is anti-debugging. There's also anti-static analysis, which is mostly by obfuscating your code as much as possible. And a mixture of the both will make the binary really, really hard to understand. I wrote a research paper on anti-debugging. I can send it if anyone is interested, but it's a little bit advanced. Yeah, we can talk about this after the lecture if you guys are willing to. We have also obfuscation. There is a lot of types of obfuscation. The best one of them is reading your friend's code. Nothing is more obfuscated than this. Yeah, just make your code so bad no one can understand it. Yeah, I'm just kidding. There is multiple obfuscators that you can find online, or you can write yourself. There's also some specific algorithms that do it. Sometimes they are mathematical. For example, instead of doing, I don't know, A XOR B, you're just going to do some Boolean arithmetic to make it more harder. Okay? You guys know what is Boolean arithmetic? Okay, it's AND or XOR, and yeah, these are Boolean arithmetic. So if you have a 1 bit and 1 bit, it's going to give you, yeah. If you have 1 bit or 1 bit, it's going to give you 1 bit or 0. Yeah, 1 bit XOR 1. Yes, this is Boolean arithmetic. You just try to make it as much complicated as possible. Yeah, and also solving the challenges start by understanding the obfuscation technique. Sometimes you have to write your own deobfuscator. I'm telling you in advance, you will have to write your own deobfuscator for the CTF, for the Cybersecurity Day. It's not really complicated, but it's not super easy. You need a little bit of Python skills, and you need to spend a little bit of time understanding how this obfuscator is working. Okay? So obfuscation is one of the techniques. This is one of them. This is an example. It's from, I just found this picture online. All the pictures that I'm using here, they're taken from multiple sources. None of them is from me. As you can see, here is like a code, how it looks like normally. And this is like the obfuscation. As you can see, it's changing the variable to this weird symbols or weird names. It's really hard to grasp what it's doing. You can further obfuscate this, for example, you will make strings base 64. You guys know what is base 64? It's a type of encoding. Encoding means changing stuff to something else, which will be two ways. So you can encode and decode. Okay? So this is just an example. This is also an example of obfuscation in C. This is really a piece of art. You can find this article here. So basically, this code here actually generates this. Isn't it amazing? Obfuscation is really an art, and I love it. Q&A. Do you guys have any questions? Yes. Yeah? Give him his mic.
Do you still have a life if you are a reverse engineer?
Actually, I don't. I mean, just imagine working full-time, then part-time here, then preparing your lectures, then at the weekend playing CTF with my team. Yeah, I don't have a life, but I try to make some time. Yeah, now it's your turn. I made 2 challenges. It's also going to be the break, so you guys going to do this during the break. I've been working non-stop the whole week. You guys have to work non-stop now. There is 2 challenges, and they're like the same repo. I will show you guys. There is one in C. Okay, going back here. Going to Rev. You will find challenge 1 and challenge 2. Challenge 1 is basically a binary, and challenge 2 is basically just a Python obfuscated code. I can show you here. As you can see, it doesn't look pretty, but your job is to get me the flag. The first one to find both flags will get lunch, or if one of you guys, or nobody found both of them and someone found only one of them, I will pay for your lunch, okay? So just clown the repo and feel free to try it out. Start with challenge 2. It's much easier than challenge 1. I think, no, actually challenge 1 is much easier. I don't know, both are easy. If you find the flag, just let me know. And this is the break time. Okay, I hope you guys were having fun. We will give the microphone to 2 or 3 people to tell us about their solutions. We have a winner, and we have 2 winners actually, and I'm gonna pay for their lunch. They deserve it. Good. Can you tell us first? You will tell us how you solved challenge 1, and you tell us how you solved challenge 2. Yeah, it was late. I mean, I'm talking about the first people that solved it.
Okay, so for the first exercise, the challenge executable, I went through it with GDB,
Nice.
step by step, starting from main. And once you get to the comparison with the value in input string, or before, it will show you the data address of which value you compare to see if it's correct. And the value also shows you, the memory address also shows you the value, of
Good,
course.
good,
And then
good.
you can see the flag.
This is a way to do it. He did it dynamically, so he did it through GDB. Someone else here did it statically, and I want you to talk about your solution, which was static.
I decompiled it, and I saw that there's basically 2 relevant functions. One, the main one's obfuscates, I
Yeah.
think. And in the main function first, there was some magic string that was copied for, I think, a length of 0x14 or something into a buffer, and this buffer was given with another magic number into a function, and in this function, the buffer was XORed with this magic number, and the result was basically the input that was supposed to be.
So he used basically one of the quirks of XORing. If we have A and we XOR it with a number 1, the results, let's say A XORed with B is equal to C. If we XOR C with B, it's going to give us A back. That's one of the quirks of XOR. It preserves the informations, even though it's obfuscate, kind of. Okay? So these were the 2 solutions. Did anyone did it in a different way than these 2? Okay, good. Now for the second challenge. How many people solved the second challenge? The one who solved it, raise your hand. Second challenge. I think someone else solved it here. You solved it? You solved the second challenge, right? I'm pretty sure someone showed me the flag of the second one. Okay. You tell us how you solved the Python challenge?
So basically, we had that that string, basically that bit.
Yeah.
On the end. Ah, yeah, there's this. Yeah, there. And basically, it's you have to reverse the string and have to do a XOR operation on it, and then you not decompile it. You how you call it that?
Reverse it.
Reverse it basically to a string, so readable characters.
Yeah. So
And
again,
turns out,
I can show you guys solution. I have it also here. So basically, these solutions, you take the target back, you reverse it again. I mean, we see it here. Okay, we see it here that we are actually reversing the string here. So you reverse it back, and then you just perform the actions in order again. So in the difference, and also if you had a plus, you just change it to a minus. And XORing, as I said, it just preserves the informations and can be both ways. Good? And this should just give you the flag directly. Good job for people that solved any challenge. People that didn't, also good job. It always starts from somewhere. I'm pretty sure the ones that did solve something did Pico CTF during the week, or am I wrong? Who did Pico CTF during the week? Guys, we need more action. Come on, more action. Nice. Okay. So that was the second challenge. First challenge. I can also show you the source code of the first one. So basically, we have like a flag which will be XORed with like 42, and then if you go dynamically with it, you can view like the parameters of string compare, and you can know directly what is the correct flag. Otherwise, you just take this string and you just XOR it back with this 42. every element. This is the second solution, so the static one. Okay? And with this, we are done with reverse engineering, and now we will start with the fun stuff. Forensics. Forensics is about a lot of rabbit holes. You always find yourself somewhere, you think you figured out something, but you did not. Like this guy, he thinks this is a murder, but it's not. It's actually here. Don't be like him. Always try to follow the leads. Don't jump into conclusions until you see something. So what is forensics? From last week, do you guys remember anything? Does anyone remember anything? Okay, there, Mike?
Hi.
Yeah, it's working. It's working.
Forensic is to find the evidence of a situation that occurred.
Yes, so forensics is basically looking for clues and trying to find evidence or trying to find some leads that will help you understand what happened before. So it's always happening after the breach. I mean, here we're talking about digital forensics, which is happening after a cyber attack. And we're just going to try to understand what happened, how did this happen, where it did go wrong, and who is the victim and who is the attacker. So it's the ability, a friend of mine told me this, he's from my team, he told me that it's the ability to distinguish between what is normal and what is not in a system. So as simple as this. This is what makes a really good forensics guy. He always tries to find where is the sus stuff in a system. It's about finding clues. It has different subcategories. There is network forensics, there is disk forensics, and there is memory forensics. These are just some of them. There is some other types, but these are the ones that we're going to take a look into today. When we are talking about malware forensics, we are always combining all of the three. So you have to take a look into what did this malware do in the system. So you're inspecting the memory dump of the system. We're going to understand what is a memory dump in a second. We have to also understand what did this malware do to our system. This requires a deep knowledge of our file system and also the inner workings of our operating systems. Also, the network is about traffic. So, for example, or most of the time, the malware will try to communicate with the attacker server or the attacker side because it will either be exfiltrating something, or in some other case scenarios, it might be a ransomware, which its job is basically to just encrypt your data until you pay a ransom. Is it clear? Also, it's a tool-oriented job. It's about literally about knowing as many tools as possible. There's basically tools to do literally everything. However, it's always good to know how these tools are working in the background. We will take a look into one of the tools in network, but it's always preferred to try at least to do this kind of stuff manually before you do it with a tool. So again, it's a tool-oriented job. Just try to automate as many stuff as possible. And last but not least, steganography is not forensics. Also, steganography is not crypto, okay? Just to make things clear. Does anyone here not know what is steganography? Does someone here know what is steganography? Okay, Mike here.
It's a way of hiding stuff in other stuff.
Exactly. As simple as this. Steganography is the art of hiding stuff in something else. For example, you can hide text in a picture. It should not be visible, and it's used to transfer information in a secure way, but it's not. So that's what they say. Yeah. So again, steganography, it's not forensics and it's not cryptography. But some people just put challenges related to steganography and forensics. Yeah.
Which category is it considered?
MISC. Yeah, or a separate category for people that actually enjoy doing steganography. Because it can be easy and it can also become complicated. If there is an algorithm that hides specific bits of something in your picture. There's also the least significant bit algorithm. I don't really recall exactly what it's called, but it basically just modifies the bits in an image and to hide something. Okay. We will start with the network forensics. Network forensics, it's the analysis of network events or traffic. It requires a good knowledge of major protocols. You need to understand how these protocols are working and what they're doing. What is a DNS, what is HTTP, what is HTTPS, TCP, UDP, DHCP, and ARP. These are just one of them. You have to actually know and understand how each one of these are actually working. Otherwise, you're not going to understand the traffic, as simple as this. Yeah, also it requires a good knowledge of the OSA model and the TCP/IP model. Do you guys know what is this? Yeah, mic here. Here.
It's different, like layers of networking. They are on the hardware level, on the lowest one, like really cables or yeah, wireless relations, and they go up till to some encryption or not encryption, but like the encoding and decoding in various standards that anyone can understand each other, and they are sometimes stateless, sometimes state-based, and so forth and so forth. How deep shall we go?
Good. Yeah, so as he said, OSE model is the way the information is transmitted between two computers, two servers, server and a client. Doesn't matter how we want to imagine this, and it goes through layers. We have the OSA model, which is the standard model, but it's not really used in the real world. Mostly in the real world, we use the TCP/IP model, and it basically defines the layers that our packets or our traffic goes through to reach the other party. It goes from software to physical, and then again from physical to software to reach his computer. Okay. You also require a knowledge of this if you want to dive more deeper into this kind of stuff. Also, one thing that I always like to mention, and also what I mentioned before, it's good to automate stuff, but you always have to understand how you can do stuff without. And what I mean without manually. One of the things is to learn how to do network file craving. Do you guys know what is network file craving? Basically, when you transfer files through the network, they're transferred as raw data. Being able to actually figure out which protocols are actually transmitting data and be able to retrieve them back is something really valuable. Because sometimes you have encrypted traffic and you have to retrieve the encrypted traffic and then somehow find the key and then you can decrypt it. Okay? So learn how to do this manually before taking a look into tools like Network Miner. If you have encrypted traffic, you always have to find the leaked key. Sometimes it's leaked in the communication. Sometimes it's leaked somewhere else. For example, in a memory dump, if the specific malware was encrypting the traffic itself. Okay. Yeah. So that's the name of my friend who helped me make these slides and also the challenges. Yeah, last but not least, it also helps in investigating the malware communication. We will start with a small demo of network forensics. We're going to fire up Wireshark. Do you guys know Wireshark? This is Wireshark, and it allows us to inspect the traffic. We're going to take a look into the Wi-Fi traffic. As you can see, it has a lot of stuff, but we don't want to take a look into this. Okay, we can run. Let's leave it run. No, I don't want to save. Let it run for a little bit of time. As you can see, it's generating different types of protocols, but with filters, you can filter out what you are seeing right now. For example, we can filter only ARP, like we talked about this. You can also do it from here. You do follow. Okay, maybe sorry, TCP. You do here follow, and then you follow TCP stream, and this is actually allows you to follow the TCP stream. Here there is nothing going on, but we are filtering it here, you see? These are the two packets that are using the specific filters, and yeah. it's really good to learn how to filter out traffic because most of the time there is a lot of stuff generated along the way. Okay, there.
Hey, how important is Wireshark to learn for forensic?
Sorry?
How important is Wireshark to learn? How important is it to learn for forensic?
It's like learning C to write C code. Well, you have to learn C to write C code. I mean, if you don't do it with Wireshark, you can do it with T Shark or TCP Shark. I don't know. I forgot the name. But there's a command line tool. I think it was called PCP. Yeah, there is TCP dump as well. There's also T Shark, which is just the command line version of this, and it also allows you to script some stuff. And yeah, we will take a look directly into a challenge. I'm gonna because we don't have enough time for you guys to do it alone, so we're gonna do it together. You can redo this stuff when you are home. Download. Okay. Oh. Okay, so this was the traffic generated by a friend of mine. This is basically a challenge. As you can see here, we just see the normal protocols that we know. We have ARRP, we have TCP, we have HTTP, and that's it. As you can see, with just a little bit of knowledge, I mean, just from reading this, we understand that TCP is actually trying to get a challenge.zip. You see? It's actually trying to get this back, and it actually retrieves it back. You see, it's a zip file. Now, our task is to basically take this thing back and see what is going on there. Like, what is this challenge.zip file? To do this, there is multiple ways. One of the ways, which is the way we're going to explain today, is how to do it manually. So you're going to go to TCP here. No, not this. This. Let's follow the traffic. Let's follow the traffic. If we follow this here, HTTP stream, as you can see, the GET request, which was the request that was requesting this, was running wget. So it was downloading this, and what it was downloading was actually able to be downloaded. As you can see, it's a 200 status. Okay, it was downloaded, and this is basically the file that was downloaded. It is just raw here. I mean, we can see it in ASCII, but we will soon change it to raw because we can clearly see that this zip file actually has the flag that we are looking for. So we're going to change here from from ASCII to raw, and from raw we know that this the first part is basically the gets, the first get. Are you guys following up? The first get request was this red. The second blue one was just the receiving status, and this is actually the file. Now this thing here, we're just going to copy it, and we're going to go to CyberChef. CyberChef is basically a tool to cook in the internet. We're just going to give it here as input, and we're going to go here from hex. Just going to read this as hex. As you can see, this is the content of the file. Just we cannot read it because it's compressed, and we're just going to download it like this. It's downloaded, as you can see. And when we try to open it, it's actually asking for a password. And this is pretty common. So, do you guys know how we can break this password? How we can break some stuff here? Brute force, yes. Do you guys know any tools that allows us to brute force this kind of stuff? Yes, good job, good job. We have the two favorites ones, or the two most famous ones. We have Hashcat and we have John the Reaper. We will use, okay, I'm gonna at least try to use John the Reaper now. And also, do you guys know what is rockq.txt? Give him the mic. Tell us about rockq.txt.
rockq.txt is the largest leaked database that contain user information that are real.
Yeah.
And it's
yeah.
used to breach force stuff.
Yes. So basically this rock.txt is basically has the most famous password, most famous stuff that you can be brute forced, especially the common passwords. Here, the password was Venus 123. You can run it. We don't have enough time. That's why I didn't run it. But yeah, as you can see, I did decrypt it. I did open it, and this is the flag. You can rock me. Nice. That was the first challenge. As you can see, it's about following the TCP stream. You can see here actually what was sent, and now because the traffic was not encrypted, we could directly retrieve the data. And yeah, it wasn't encrypted. Do you know why? Because here we have HTTP, and it's not HTTPS. HTTPS is encrypted. Okay. So that was the first demo or first challenge. We can continue. Sorry, we don't have enough time to dive deeper into this, and but you get the idea, right? Second thing is disk forensics. It's about recovering also deleted files, recovering deleted partitions. Do you guys know what is a partition? Guys, you did Born to be Root, right? You should know what is a partition. I assume everyone knows it. If you don't know it, Google it. The second thing is about metadata timestamps. Do you guys know what is metadata timestamps? Yeah, just say it. Okay. Exactly. So basically, he said it's when the last time a file was edited. This is actually correct. It's basically the data that tells us when the file was edited, when the file was created, when the file was deleted. These are valuable informations because if we see that a specific process is doing some weird stuff, is creating some files and deleting some files, we know that there is something suspicious there. Disk forensics also about hiding unencrypted data. Sometimes you get to know an encrypted partition that you have to decrypt. Sometimes you have some encrypted files where you have to find the key to decrypt and other stuff like this. Also, this is really heavy oriented to the specific file systems we are working on. I have on the repo, you can do this at home. I have linked a challenge which was meant to be a reverse engineering challenge, but it was basically a compressed image of Linux, which you can try to decompress yourself and see through the file systems and so on and so forth. This is one of the examples. It can also be in Windows, where you have to take a look into the Windows registry and look at the events and stuff like this, okay? Last but not least is Mac. It is the least one you see so far, but it's also available. So yeah, disk forensics is just oriented towards which operating system we are working on or with. There's a lot of tools you can use. There's Autopsy. It's not Autospy. It's Autopsy. Oh, Autopsy. There's also FTK Imager. There's LifeKit. There's a lot of tools that help us see the hidden files, also the deleted files sometimes. And yeah, sorry we cannot do a demo here, but as I said, there is already in the repo challenge. You can just try it out yourself. Yeah, this is a picture of Autopsy. As you can see here, we can see like files, hidden data, and stuff like this. Yeah. Also the timestamp on the left. Last but not least is memory forensics. It's about analyzing volatile data. You guys know what is volatile data? Please.
Basically, it gets removed once, so it can be changed very easily, and it gets removed.
Yes. So volatile data is basically data that can be modified and changed. It can also be called non-persistent data. Some example of this is basically the core dump of a process, what is running in the RAM, what is running in the memory on the runtime. All of this stuff can give us an idea what was this process actually doing when it was running. And memory forensics is about this. So you have to inspect a memory of a running process most of the time after it's done. I mean, we are just going to inspect the memory dump of it, and you have to find evidence out of this. There is some artifacts that we go through. There is, for example, you have to take a look into the running processes because not most of the time, but sometimes we have the memory dump of the whole system. And in the memory dump of the whole system, you basically have the running processes and the threads. There is some specific flags. Here there is a tool called the volatility 3. It's the third version of volatility. This tool literally allows you to do everything. It's like your way to go. You can use a command called PS list. This model will allow you to list the running processes. There's also PS scan, which also shows you the hidden processes. There's also PS tree, which PS3, which shows you the processes as a tree. So you see parent and the child relationship between them. There is also some other flags. I don't remember them by heart. I always use the help menu. But let me just take a look quickly because I noted them. This is my friend Abdurrahman, the one who helped me do this. So we have PS scan. I will just make this bigger. Can I? Okay, cannot. There is malfind, is to find the injected code. And we have also file scan for retrieving all the files. All the files. And there is dump file. File scan basically tells us the files that were accessible by a specific process. So let's say this specific process was trying to access a specific path or this specific file. This file scan will tell you which files were accessed, but it's not going to give you these files. It's just going to give you the address of this file in the memory dump. Because when you run a specific binary, it will be always loaded on the RAM. You guys know this, right? And then we have the dump file command. The dump file will allow you to dump this specific file that you saw there, just by knowing the address. And also we have memscan. You give it the PID that we did find in PS scan or PS3 or PS list. You just give it there, and then you can just dump the process. And when you dump the process, you have basically that specific binary. Okay? Yeah, this is it from this side. Yeah, so it also helps us detecting the fileless malware. Fileless malware are basically malwares that run fully on the RAM. They don't have any file related to them. They don't have a binary which you have to run, then they will be running. We are also asked sometimes to extract credentials or encrypted key. Let's say we have an encrypted traffic, but we find a suspicious behavior of the malware, which was basically decrypting the traffic with the key. You go through the memory dump to identify where is the key and then use it to decrypt the traffic for further investigations. Yeah, so in the end, if you want to summarize everything about the disk, memory, and network, it's about reconstructing the user activity. We want to know what did the user do throughout this whole thing, like throughout this breach or throughout this specific attack. That's our end goal. And yeah, as I said, the volatility is your way here. You can install it, it's just Python. There is a GitHub repo. Just get it down and install it. This is their logo. Sorry that we didn't have time to do it ourselves, but there is a challenge. You can try to solve it yourself. I will tell you the description, because without description it will be a little bit hard for you to know. The description is this. I wrote something and they told me that it's in base. This is description. And it already has a lot of hints. Okay? So use volatility, use the command that I told you before, and it should be way more than enough to solve the challenge. Yeah, so is this really the real world? Yes and no, or yain. Basically, this is some stuff that we do, but it's not always the only thing. You always have to also go through the Splunk logs. You also have to go through multiple sources of logs to understand the behavior. As a forensics guy, you don't always have to investigate breaches. Sometimes you just have to investigate some weird behavior, something weird happened in your system, and you just want to figure out what happened. It doesn't have to be always malicious. This is it. Yeah, so again, going back to the same idea, the real world stuff is an intersection of everything. So you need a little bit of network forensics, a little bit of the disk forensics, a little bit of memory forensics, also reverse engineering. Let's imagine you found a malicious binary that was downloaded. Now your job is to basically decompile it and understand what it's doing. Also, most of the malwares are actually written in either C or a low level language. because it's fast and can be stealthy. Yeah, also it's an intersection between Rev, practical crypto, which means traffic is encrypted, you have to know how to decrypt stuff, and digital forensics. So this is like your daily life job. What do we have? Yeah, any questions related to forensics? Here, Mike, please.
You just said that you have to know how to decrypt stuff, and
It's working, just get closer.
so how would you decrypt it if it's using like unbroken algorithm?
I mean,
for example, elliptic curves or something advanced that cannot
if you
be
have a
broken.
key, you can decrypt it.
So you need to find the key.
Yes. It's like here, the crypto, why I wrote practical crypto and I didn't write crypto. Practical crypto means just knowing which algorithm is this, how it was encrypted, and how to decrypt it. That's it. Decrypting means the key already exists. You don't have to actually know crypto to break the algorithm. You don't have to break the crypto system. You only have to do a direct decryption. You're just going to do what's the server on the other side where you are sending the data doing to decrypt the data to understand what is going on. Because the computer also have to understand the data. The computer also have to encrypt the data. You understand what I mean?
Yes.
Yeah. Any other questions? Okay. So again, normally, yeah, okay, sure. Yeah, sure. Also, if you're really interested in forensics, I can forward you this link. This is like the guy who did help me do this. And he actually wrote a really advanced forensics article for SANS. Do you guys know SANS? It's one of the biggest firms related to cybersecurity. And he wrote them an article. It was published on their main website. You can check it out. I can also put it in the GitHub repo. And these are the commands. Yeah. Here. Good. Go back here. Yeah. So try to do the things that we didn't do today. Try to also redo the challenge, the pickup challenge yourself at home. If they are under the repo, I'm not gonna modify them. And thank you for listening. Before you go, for next week, we're gonna have binary exploitation. Again, bring your laptop, and now you can rev. So for people that find some difficulties using GDB, try to experiment with it. Also, I'm saying this again, try to install pound debug and use it with GDB. It will make your life 1 million times easier. Again, pound debug or Jeff or any other plugin that helps you with your reversing. Try to have this, experiment with GDB, because last week I'm telling you guys, you're not going to understand what is going on if you don't know how to use GDB. It's really important, because now we're going to go from just understanding how it works to understanding how it works and finding bugs. Okay? So next week is about binary exploitation. Please watch some videos related to shell coding, a little bit of assembly, and the binary exploitations, so that we can actually move quicker forward. Because we can do it extremely beginner friendly, but after 2 hours, we're going to realize that we didn't understand anything. We didn't do anything advanced. We want to go through the advanced stuff. That's why please try to do a little bit of work. Also, try to do a little bit of binary exploitation challenges on PQCTF and the Pound College. Pound College is basically your university for Pound. It's really, really well designed. It's maintained and created by Arizona State University in the US. And the challenges are great. The infrastructure is great, and it's completely free. Like, you don't have to pay anything. And they also have the workspace where you can work. So you don't even have to work locally. So please, please, please try to take a look into these stuff. And I was going to say you are free to go, but I still have to take a look into how many Pico CTF challenges did you guys solve? Did you finish the 20? Did you finish 110? Okay, good, good. Okay, good, good, good. You are free to go now. Thank you for your time and attention, and see you next week.